Okay, so yeah, crystalline solid. Okay, I just start with the crystalline solid. Okay, packed in periodic. Okay, in 3D arrays. Okay, possess a well-defined shape such as a metal and alloy, metal ceramic, and some polymer. Okay, this is a long range. Okay, it's well defined. Okay, for non-crystalline is a non-periodic packing or short range order. Okay, complex structure and rapid cooling. You can see here. For example, like a water, right? Water has a short range order. Okay, one oxygen atom can covalently bond with two hydrogen atoms, but the order disappear when each molecule is bonded to other molecules. Okay, through the secondary bonds. So that's why we call it a short range order. Okay, so we call it also amorphous non-crystalline. This one. Okay, so the atomic arrangements in the metals, okay, the atomic arrangement we can describe by referring the atom to the point of the intersection. Okay, a network of line in 3 dimension. If you look at here, this is the 3 dimension. This one. Okay, we call it a space lattice. Okay, atomic arrangement in crystalline solid. Okay, this is the atom to point intersection of the network in line in 3D. We call it a space lattice. Okay, so what is a space lattice? Okay, it's an imaginary network of line in 3D. Okay, intersection of the lines lattice point. Okay, represent one atom. If you look at here, this is represent one atom, and there is an infinite number of lattice point. Okay, generally atoms in the crystalline solids occupy the lattice point. Okay, so this one. Okay, if you look at here, the repetitive subdivision. Okay, for the space lattice, we call it as a unit cell. This is another unit cell. Okay, unit cell, another unit cells. Okay, to form a space lattice. Okay, okay. So this is a lattice point. Okay, this is a lattice point. Look at here, one atom, one atom. Okay, this is a space lattice. Okay, this point, and this is a unit cell. Okay, so block of atom which repeat itself to form a space lattice. Okay, the definition of unit cell, smallest subdivision of the crystal. Okay, and unit cells are building block of the crystal. So if you arrange all these unit cell, is become a block of the crystal. Okay, okay. Let's see the definition of the unit cell also. Okay, so this one. Okay, if you look at here, the unit cell have interaxial angles or angles. Okay, and this one also have different length. Okay, so this is, we call it as lattice constants. Different cells have different angles as well as length. Okay, you have to remember. So there are 7 unit cell system. Okay, a variation of this lattice constants. Okay, so different of the length. Okay, as well as the angles. So let's see these 7 unit cells which is generally available. Okay, metals, actually metals are pure metals, easier to describe. Okay, identical perfect spheres. Okay, look at here. Okay, and also only one type of element is present. Okay, all atomic radii are equals. Some case of the structure of the inert gas are very low temperature. Okay, and the most thing is the metal have a simplest crystal structure. If you want to learn, so we need to know the simple crystal structure, which is cubic. Okay, they have a BCC, body center cubics. Okay, so why we focus on the metal? This is the important. Okay, only seven different unit cells. Okay, according to Bravais, which is a 14 standard unit cell, can describe. Okay, for basic types, okay, of the unit cells is a simple, body centered. Okay, this one, if you look at here, a simple cubic is they have 4 atom here. Okay, one, not four, eight, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Body center. There has a body center here, one atom here, in the middle of the unit cell. Face centered. 1, 2, 3, 4, 5, 6. So that means 6 atom. Okay. 6 atom centered in every plane. Okay. So you have to remember they have 6 for face centered. And base centered have two opposite side. 1, 2, this one 6. Okay. Body centered they have 1. And simple cubic centered they have no body centered or atom at the plane. You have to remember this is a basic type of the unit in itself. Okay, so if you look at here that the unit cell, as I told you, different in their angles as well as the length. Okay, for the cubic unit cells. Okay, so if you look at here that the angles. Okay, the angles A of alpha, beta, gamma is equal to 90. Okay, if you look at here, this one is gonna be it is 90 degree. Okay, and the length is equal. A, B equal to C. And they have a simple, this is categorized as body centered as well as face centered. Okay, this is what we call it as cubic unit cell. For tetragonals actually the length is different or the height C. Okay, this one. But their angles, okay, it should be similar, 90 degree. Okay, only the height is different. Okay, this one is tetragonal. Okay, orthorhombic and rhombohedral. Okay, orthorhombic and rhombohedrals. Okay, the length is not similar. Okay, A, B, and C is not similar, but the angle is same, 90 degree. While rhombohedrals, the length is the same, but the angles for gamma, okay, only for gamma is not equal to 90 degree. Only alpha and beta. This one is rhombohedral. Okay. We have a hexagonals, okay, monoclinic as well as triclinics. Okay. This one is A not equal to B not equal to C. Okay, because it's hexagonals, but 90 degree. Okay. A not equal B not equal to C. Okay. For monoclinic as well as A not equal to for triclinics. But alpha and beta as well as gamma is equal to 90 degree. Okay, they have a simple for hexagonal, monoclinic, simple and base centered as well as simple for triclinic. Okay, of metallic crystal structure, what I want to tell you is 90% of metal have either body centered cubic, okay, 90% and face centered cubics. Okay, hexagonal close pack crystal structure actually we're not gonna cover in this course. Okay, so we're gonna cover only this one. Okay, body centered cubic, face centered cubic, mostly this one. Okay, so please remember FCC. Okay, they have atom on the plane of the cubic on the cubic of the unit cells. Okay, on the unit cell, this one they have 6, while for the body centered have 1 atom on the center of the cubic. Okay, you have to remember that one. Okay, cells analysis. The question that we have to answer is, what is the basic structural parameter? Okay, lattice constant or side of the cubes. Okay, what is how many atom per unit cells? How many atoms packed in the unit cells? Okay, how many volume per unit cells? Atomic packing factor. What is the definition of the atomic packing factor? Closed pack direction. What is the coordination number? Is different between body center cubic. Okay, face center cubic as well as simple cubic of your unit cells. Okay, what is the relationship between lattice constant A as well as a radius? Okay, before you calculate the atomic packing factor, okay, before you calculate this atomic packing factor, you have to know what is the relationship between radius as well as a lattice constant. What is the linear densities as well as planar density? I think this one we're going to cover linear and planar density in the second part. we discussed, I think, until the atomic packing number as well as the close packing direction. Okay, not, I think this one, yes, until the coordination number as well as the lattice constant. Okay. Coordination number, the definition is the coordination number of the crystal structure is the number of the neighbors. Okay, if you look at here for the cubic center, okay, so this one, the neighbors atoms, they have how many? 6. 1, 2, 3, 4, 5, 6. Okay, so it's cross. Okay, so one atom directly touch 6 other atoms. So that means for the BCC, they have a 6 of number of neighbors. Okay, so the coordination number of the simple cubic have 6. Not body centered. This one is simple cubic. Sorry. Okay, simple cubic is different. Okay, because this one is for simple cubic. Okay, this one is for simple cubic. Sorry. Okay, so for the simple cubics, okay, they have a coordination number equal to 6. Okay, for body. Okay, so how to count the number of atom per unit cells? Okay, at corner have 8 cells, so equal to 1 per 8 atom per unit cells. Okay, if you cut here, you can get 1 per 8 atom per unit cell. I'm going to show you how can be how this corner have a 1 over 8, okay, or 1 divided by 8. H, okay, H have a 1 over 4 atoms. Okay, face 1 over 2. Okay, body 1 atom per unit cells. You have to remember that. Okay, for the body, because its center is 1. Okay, on the face they have half. Okay, this one half. Okay, so if you look at here, how many atom per unit cell for the body center cubic, face center cubic, we're going to see how many atoms per unit cells. Okay, simple here, simple cubic unit cells. Okay, so simple cubic unit cells, look at here. Okay, number of atom per unit cell is equal to 1. Okay, and then volume of atom per unit cells. Okay, if you look at here, based on the 1 unit cells, which is sphere. Okay, 4 divided by 2 pi r power of 3. Okay, and atomic packing factor is equal to 0.52. Okay, or 52% is packed with the atom. Okay, and the rest is the voids. Okay, and close pack direction is equal to direction where atoms are continuous contact along the cube edge. So please remember that the coordination number is equal to 6. Okay, why is the number atom per unit cell is equal to 1? So let's we see this video. Okay, okay, I will share this video. Okay.
To explain the bonding and structure of metallic crystals, we assume that the atoms are spherical. The spherical atoms can be packed together in different arrangements. Some arrangements are more efficient ways of packing spheres than others. Simple cubic packing is 54% efficient. 54% of the space is occupied by atoms, while 46% is empty space. This is the first layer of a crystal with its atoms arranged in simple cubic packing. Click on the second layer button to see how the second layer stacks in simple cubic packing.
Okay, this is the first layer. Okay, let's see the layer.
The second layer of atoms stacks directly on top of the first layer. Click on the third layer button to see how the third
Is the
layer stacks directly on top of the second layer. All layers of atoms in simple cubic packing are identical. AA, because all the layers are identical.
so let's see the user.
The smallest repeating unit of a crystal lattice is called the unit packed structure.
So how many atom, right? So see,
A corner atom or sphere is shared by 8 unit cells. Thus, only 1/8 of a corner atom lies within a given unit cell. In a simple each of which has one per
how what of the yeah, can you hear? Okay, so I share this one. This is the video. See, so we zoom in. Okay, there's no sound for this video, and then okay, you cut. This is one unit cell. See, 1/8 at the corner. So when you arrange the unit cell, okay, see the corner is equal to 1/8. So and then you rearrange again. So equal to one atom, one particle per unit cell. So okay. So this is a coordination number. Touch with the center of the atom. Okay. So for the simple cubic is equal to 6, the coordination number. So they have a 6 neighbors. Okay, again. This video I think is quite good. But there's no sound. Okay, so this is the void, or which is not based on the atomic packing factor. Okay, only 52% is packed with the atoms, and the rest is void, or there's a space. Okay, so this is a simple cubic. Okay, so I hope you can understand about the simple cubic structure. Okay. Okay, so I repeat, number of atoms per unit cells. So you have to remember for simple cubic is equal to 1. Okay, and the volumes is equal to the one sphere. Okay, and the atomic packing factor, which is occupied by atom or hard sphere, equal to 0.52 or 52%. Okay, and coordination number is equal to 6. So this is for the simple cubic. Okay. Okay, so how to calculate the atomic packing number? Okay, which is occupied by the matter or the atoms. Okay, so if you look at here that atomic packing factor is equal to volume of atoms inside the unit cells. Okay, this one divide by the volume of the unit cells. Okay, this is the volume of the unit cells. This one is the volume of the atom inside the unit cell. Okay. So atom unit cells, okay, you remember, okay, for the, okay, and then the volume of the atoms, okay, similar to the sphere, okay, 4 divided by 3 pi r power of 3, and divide by volume of the unit cells. Okay, how we can get this one volume of the unit cell? If you look at here, okay, this one is, if the length is a, this one a, what else, and this one a. Okay, a times a times a is equal to a power of 3. Okay, so from this one, if you look at here, r3, okay, is equal to 0.5a. Okay, so because the r, right, for the a. Okay, so 0.5a. Okay, so just cancel out, we can get 52%. Okay, so that means atomic packing factor is equal to volume fraction of the cell that is occupied by matter, only 52%. Okay, and the rest is the void or some space. Okay. Okay, so why is one atom unit cells, as you watch from the video, is content of 8 times with 1 divided by 8. Okay, at the corner, all the corner, this one. Okay, so it is equal to 1 atom per unit cells. Okay, so this is how to calculate atomic packing factor for the simple cubic. Okay, so you have to remember this one. Okay. Okay, any question about the simple cubic? Okay, simple cubics. Okay, this one a is equal to 2r. Okay, look at this one. Is this one is 1r. So 2r. A equal to 2 and r equal to r. So you just substitute here. Okay. Okay. So for the basic, that's the video. This is a body centric because there is a one.
To explain the bonding and structure of metallic crystals is
Okay, this one. This one. I'll show you the video. Okay.
Dokter, sorry.
Yes. Yeah. Yeah. Apa dia?
I want to ask, Dokter. I want to ask.
Is it?
Tadi tuh
Yes.
R equals to 0.5A, right?
Yes.
Why there is an A in 0.5? Itu ada A.
Right. Actually, we
Yes,
A is how to say, we did not define in the unit of centimeter, right? We define the unit of C, right? Isn't it?
Kenapa dokter? Lagging dokter.
B or C. Wait. Is it okay now? Is it okay? Hello?
Sorry, your sound
Okay tak?
not clear dokter.
Not clear. How about this one? Is it okay?
Yes.
Okay. So if you look at here, okay, why actually it's based on the definition. It doesn't matter if you want A, B, or C. It's just a length. If you want to use
Oh,
L also is possible. Okay?
just
Faham tak?
definition.
Yeah, definition.
Oh, I
Based
thought
on this,
there is
yeah, this
something.
one if you L, you use L or L, right? It's just like a symbol because
Oh,
we didn't measure exactly the length of the atom. How you measure, right? It's just based on the unit and based on the what is it, character, right? L or you want to use B, it doesn't matter. But the most
okay,
important
okay.
thing is this equation. Okay, the volume of the atoms in term of radius, right? So R is equal to A is equal to R, right? This one radius, one R, right? So that's why we can cancel out this A. If you use B, this one also is gonna be R. Okay? Is
Okay,
it
okay.
clear?
I thought there is something else, dokter. Yeah, sorry ya, dokter. Yeah, thank you, dokter. Thank you, dokter.
Okay. It's a video. Because it's because low connectivity. Okay, wait. I share this one again. Sorry. Okay. Can you see this video? Anyone? You see video?
Yes, okay.
Okay. So let's see for the body center
To
cubic
explain
packing.
the bonding and structure of metallic crystals, we assume that the atoms are spherical. The spherical atoms can be packed together in different arrangements. Some arrangements are more efficient ways of packing spheres than others. Body-centered cubic packing is 68% efficient. 68% of the space is occupied by atoms, while 32% is empty space.
See if you can empty space.
This is a view of the first layer of spheres in body-centered cubic packing. Click on the second layer button to see how the second layer stacks in body-centered cubic packing.
Okay, so let's see second layer.
The second layer of atoms stacks in the depressions of the first layer. Click on the third layer button to see how the third layer stacks in body-centered cubic packing. The third layer stacks in the depressions of the second layer. The third layer of atoms has the same arrangement as the first layer. This type of stacking pattern is called an AB-AB pattern because the spheres in every other layer occupy the same position. Click on the unit cell button to see the smallest repeat. Cell. Unit of a crystal layer. For the corner atoms.
So let's see. I think you can see a clear view about the body center cubic. That's the video. Okay. Finish. Sound. see body center cubic, there is a one atom at, okay. 1, 2, 3, 4, 5, 6 particle per unit cell. Okay. So that means for a body center have two particles. The Cornish number, the numbers of atoms. Right. So 1, 2, 3, 4, 5, 6, 7, 8. Over there. So this is for the clear view, the arrangement of the atoms. Okay. The total is 2 atoms. Okay. Okay. So let's see the slide. What I want to summarize here. Can you hear my voice? Sorry, there's a problem with the internet. Okay, so
Yes,
I'll try to. Okay, so let me summarize from that video. Okay, so if you look at here for BCC crystal structure, okay, it's represented as one atom at each corner and one at the center of the cube. Okay, for the coordination of the body neighbors. So example of the okay, and look at here that remember is two particles in one unit cell. Okay, so 1 times with 1 divided by 8 plus 1, so equal to 2 atoms. So atom contact each other. Okay, how to calculate A? If you look at here, that's the length, okay, in relationship with the radius. Okay, so this line is equal to A, okay, and this one is equal to A, okay, and we need to get this one, okay. So if you look at here, if we want to get this one is equal to A, right? Okay, this is equal to A. Okay? This is equal to A. Okay, to A, okay, plus A, okay, equal to, you can get this length. Okay, you can get this length. Okay, so this is equal to 3A. So 3A is equal to 4R. So the length, okay, in relationship with the radius. Okay, so if you look at here, this is 1R, this is 1R, another 1R plus 1R is equal to 4R. So 4R is equal to square root of 3A. So you can get A is equal to 4R divided by square root 3. Okay, so you have to remember that this is the length, okay, for this one, okay, or the lattice constant. So to calculate the atomic packing factor, if you remember that the general equation is the volume of atoms per unit in unit cell per volume of unit cells. Okay, so for the V atoms, this is 2 because there's a two particles in one unit cell, and this one is the volume for the sphere. Okay, so unit times with 2. Okay, so we can get 8.378 R. Okay, while V for the unit cells, okay, A power of 3 is equal to 4R. Remember, we defined this already. So it's equal to 12.32 R power of 3. Okay, so just leave this to this V atoms and V unit cells. So we can get, okay, this one we can get 0.68. So that means is 68% is occupied by the metal and the rest is the empty space or void. Okay, so you have to remember that for BCC. Okay, okay. So we already calculate the atomic packing factor for the BCC. Okay, as well as
No, doctor.
See this one. Wait for the video. Wait, okay. I got some problem with my internet. Cannot. It's okay. So we just post it. I cannot share the material actually. So it's so hard to teach online.
It's okay, doctor.
Okay. So you already have my even now is quite
Yes, can see.
just summarize with you that video. Well, communicating factor is equal. Uh, okay, have items okay, and the content one item and the latest constant is equal to 4 to okay. This equation to no, they have two atoms. Okay, half. Particle. Okay, so it's become not gamma. While the atomic factor is equal to for the FC. So talk about the simple cubic, okay, as well as BCC and FCC, okay. So just remember this equation, how to calculate the atomic factor and the coordination number also, okay. The FCC have a 12 neighbors, okay. Coordination number is equal to 12, okay. Any question before we? Actually, this have a video or tutorials. Maybe I can show you. It's almost. Maybe I can share this one. Crystal voice. I cannot share actually. Okay, can. Maybe I can. Okay.
crystalline solids. In metals, atoms occupy specific positions in the space lattice to form an ordered, repetitive, and three-dimensional pattern. Space lattice is a network of lines in 3 dimensions containing an infinite number of lattice points. Atoms in crystalline solids occupy the lattice points. Repetitive subdivisions are observed in the space lattice. The unit cell is the smallest subdivision of the crystal that retains the overall characteristics of the total crystal. Unit cells are the building blocks of a crystal. There are 7 different unit cell systems: cubic, tetragonal, rhombohedral, hexagonal, orthorhombic, monoclinic, and triclinic. All 7 unit cell systems are variations on the following cell. We will study the 3 most common unit cells. 1. Body-centered cubic. 2. Face-centered cubic. 3. Hexagonal closed packed. The body-centered cubic structure, or BCC. In a BCC unit cell, atoms are located at all 8 corners and a single atom at the cube center. Examples of metals with a BCC structure are iron, tungsten, chromium, potassium, and tantalum. Consider the BCC cell below. Each atom has the same geometric environment. Each atom has the number of neighbors is called the coordination. How many atoms are there inside a BCC unit
Okay,
cell?
BCC. How many atoms are there inside BCC unit cell? Anyone? Before we stop, I think I can give you this link. BCC unit. How many atoms? If you remember. Anyone? BCC? So you can refer to my slide. Okay, BCC.
Two.
If you refer. 2. Are you sure?
That is correct.
Yes.
Please press continue to verify your answer. At each corner of the unit cell, we have 1/8 of an atom, an octant. At the center of the unit cell, therefore, what is the relationship between the lattice constant A
Relationship.
and the atomic radius R in a BCC cell?
Anyone?
4R over Z3.
This one. Are you sure? D. Is it? Is it D? I click D.
Benar.
Press continue to verify your answer.
Okay. Okay. So we start even this video. I didn't open this one. The problem. Okay. So if you look at here, in my there's one example and tutorials I hope to this tutorial and we discuss tomorrow. Okay. So we discuss tutorials. Okay. Example 1 tutorial example 1 tutorial 1 2 3. Okay. Please do this for the problems. Okay. Any questions about this one? Any questions?
So far, no, Doctor.
Okay. If no questions, we stop here and we continue tomorrow. Thank you, guys.
Thank you, Doctor.
Okay.